Hello, assalamu alaikum to all. So, this video lecture series is for the subject digital signal processing, and this subject will be taught at Department of Telecommunication Engineering, University of St. Jamshoro. So, let's begin with the course. So first, my introduction. My name is Dr. Sandar Ali Khwaja. I am an assistant professor at Department of Telecommunication Engineering, Faculty of Engineering and Technology, University of Sindh. I have completed my PhD degree from South Korea in the field of deep learning with the specialization in computer vision applications and IoT applications. So for this course, if you have any questions or if you have any queries, just reach me out at my email address. Most of the times you can see my codes regarding different applications at my GitHub page, and maybe you can find these videos at my YouTube channel. So just reach out to me on any of these three alternatives. So let's see the lecture. We have already discussed about it. So the interactive lecture will be held on Tuesdays, and I'll be answering your questions if there are any regarding these video lectures, so you can discuss it with me, and if you have any problems, then we can just discuss those particular slides which are like uh, uh, are not understandable by you. So lectures are of course not compulsory, but they are meant to be useful. So if you will just uh, attend the lectures, it will be super useful for you for the coming subjects as well, because digital signal processing is a kind of prerequisite course for many specialized subjects. And of course you do not learn to do just by listening. So what I will encourage you to practice the codes which I will be doing in this class, so you can just run those codes and see that how you can modify them and what effects it plays on different kinds of signals. Okay, so for grade and exams, as you know that the current situation is not very user friendly currently. Because of pandemic, we are conducting these classes online, so the grades and exams are mostly set by university administration, and there is no clear guideline about this. So I'll be announcing the grades and exam policy as soon as the university administration will convey this information to us. So let's start with signals. So signals is are acquired from multiple sensors. It can be acquired from any voltmeters, it can be acquired from microphones, cameras, and so forth. Now basically these signals are just a kind of a phenomenon. It's just a function which conveys information about a phenomena. So what I am going to do right now is to review some basic concepts which you have already studied in signal and systems, and then we'll move towards the digital signal processing stuff. Okay, so digital signal processing is nothing but the discrete time version of the signal processing which you have already studied in signal and systems. We just have to understand the key ideas. So we have signals and they come from some sort of sensors, and you can visualize those signals like this is a kind of a speed signal, and this is a kind of a signal from voltmeter. Even if you see some sort of image like this and it's written there is no signal, even though there is a signal present here, so it's not like there is no signal at all. Okay, so for systems, the systems are those entities which process signals to produce maybe other signals. So for example, let's take an example of this. The example can be a kind of a gas pedal. So let's say the signal comes from a gas pedal in your car that goes through some sort of a complicated system, and the signal that comes out is the velocity that drives the vehicle. Now, this is probably a horrifying and at the same time complicated system under the hood, but that's the idea. Or let's take another example. Maybe I have a CD that encodes a digital signal. I put that to my stereo, which you guys may not use anymore, and what comes out of my speaker is sound. So it's like a one-to-one mapping between bits of information on a CD and the sound that comes out. But do not it's like the CD is a digital signal and the sound is a continuous signal. So it's like we have the digital signal at the input, and what I'm getting at the output is the analog signal again. Now, historically, this signal and systems concept has been derived from the field of power engineering. In early days, it was all about motors and circuits, that kind of stuff. So this kind of formalism is so successful in other fields as well, like equally successful, which is like chemical process control, economic models, and so forth. Now let's talk about the continuous and discrete time signal. So the key distinction of this course will be continuous time signals versus discrete time signals. We already know from signal and systems that continuous time signals looks like this, where I have a function of t and I have signals like x of t and representation such as an unbroken line that represents a signal that I can ask at any point in time. Let's say if I want to know that what is the value at 0.568, so there would be some value at that particular point. Then we have a discrete time signal, and in that case we have like function of n, and x of n will be sampled at certain fixed discrete steps. So I don't have any connecting lines that fills the gaps between these points. Basically, whenever I draw digital signal, it's going to be like this most of the times. This is a stem plot. It's like a stem command in MATLAB. You can use it, which represents what's happening at every point in time. So there is no such thing as x of 1.5. So I cannot calculate the value at x is 1.5 because it is like divided into discrete time steps. So for a digital signal, there is a lot of theory behind as how to go or transform this continuous signal basically to the discrete signal in such a way that I do not lose any information. And that's what the sampling theorem is all about. We are going to cover that in this class too, maybe in the next class. So we know that in certain conditions we can actually sample the continuous time signal so that the samples are good enough to reconstruct the original continuous time signal if you want. So in some sense you haven't lost any of the information. I'll be coming back to that later for sure. So our focus is mainly on this part as all the computers and devices are mainly digital. It means that even if we are getting an input from continuous time signals, they still need to be converted to digital first, and maybe then they are digitally processed, and then maybe they produce another digital signal, and maybe like they are processed through another digital system, and then at the end they may be converted through a DA system like digital to analog converter, which converts the discrete time signal to its continuous counterpart if it's needed, of course. But these days all of the processing inside the computer is digital. One thing needs to be understood here is that not only are the samples which are taken at the discrete spacings are a part, but also in practice I do not have an infinite resolution on the y-axis either. So for example, in this figure, let me use pen here. Okay. So in this figure you can see that I have some discrete locations where the y level matches the point like this. You will see this point matches to this point matches this thing, this point matches to this thing. So I have basically fixed intervals where the y-axis matches to the x-axis. Now this is called quantization, and if you use iTunes or other related kind of softwares, you can find the option for quantization, and you can select 8-bit symbol or 16-bit symbol, which means how fine I should discretize the y-axis. We'll talk about some of the implications as to how that works also, but like at this moment, let's just talk a little bit about processing signals. So what are the kind of basic operations which we can do to a signal? Okay, now the basic operation, one of the kind of common one, the common operation which you are going to perform is flipping, and it is also termed sometimes as time reversal. Especially if you have studied convolution, you will know about the concept of flipping. So if I have some x of n like this, and I want to look at its flipped version, let's say, let me just write it here. So if you have a kind of x of n, so this is a kind of x of n. Sorry, I'm writing with the mouse, so my writing would be very glossy and clumsy, so just just ignore my writing, but I will try to be as clear as possible. So this is the flip version, and it can be represented by x of minus n. All that means is that I am flipping the samples. So it's like flipping the samples from left to right or up to down. It's up to you. There are different commands for it. So currently what I'm doing is I'm flipping the samples around y-axis. So you will see that this sample has been flipped here and this sample has been flipped here. So it's like a mirror image. Then there is scaling. So let's use the same x of n, and let's see what x of 2n looks like. So let me just use this razor, and now this signal is x of 2n. Now what it does is it makes the signal faster. It's like, so the way I think about this intuition is that it's like saying if I'm playing an audio file, so I'm playing it twice as fast. So that means that the overall duration of the signal should decrease by 2. So that means that I'm taking every other sample so that it becomes something like this. Now here you can see that I am taking this sample, so this sample is here, but I have skipped this sample and then I have directly contributed or like plotted this signal, this sample, and then this sample is skipped to this sample, and then this sample is skipped to this sample, and similar to this one. So you will see that now previously I had a kind of 9 samples, and right now I have 5 samples. So that means that the overall duration of the signal has been decreased by 2. So one thing which is definitely true in DSP, which was not true in continuous time signal, is that we lose information sometimes. So after I do this scaling, I have thrown away the samples in between that I have, and I'll never get them back. The only way I can retrieve them back is that I sample them above the Nyquist rate. We'll talk about it later, so don't worry about it now. But in principle, for continuous time signal, I can squish it, stretch it, and I'm not going to lose any information. But for digital signal, I am definitely throwing away stuff. Let's see about the case of x and now n divided by 3. Now, again, let me just erase it so it doesn't create a confusion. Now this signal is x of n by 3. So here this means that I am slowing down the signal by a factor of 3. So the plot should get broader, right? The value at 0 will remain same, but uh, now what used to be the value at 1 will now become the value at 3, and the value which was used to be at 2 will now be at 6. So if you will see, the value at 0 here will remain same, and the value at 1 will be at 3, and the value at 2 will be at 6. So it's like going it's like I do not do anything else, but my expanded signal should look like this, and I do not have anything to put in these middle locations. So what I do is I just uh, kind of put zeros, because I do not have any samples to grab from. Now the next thing, which is another operation, the basic operation which we use extensively in signal processing and digital signal processing, is shifting. Now shifting the signal is one of the most common things you want to do. So it is actually represented by something like xn minus n naught. So this means that in this case I have if you will think about it, the n naught is always an integer. Okay, so if I want to shift my original signal by 1 units, I can just write this as x n minus 1. So this 1 tells me how much I am delaying my signal. This simply means that the signal should start 1 unit later. So let's say if I want to know the mapping, I can use something like y of n equals to x of n minus 1. So if you just plug the values, like let's say you plug the values y of 2, this becomes x of 1. So this is 2 minus 1, this becomes x of 1. So if you will see here, I have actually delayed the signal. So this is at minus 3 and this is at minus 2. So the signal is shifted by 1 unit. And if you will see that the y of 2, which is this one, is x of 1. So you can actually verify that. And if you will compare here, you will see that the point at 2 in the delayed signal is the point at 1 in the original signal. So if you are really not sure whether you are shifting the signal the right way, then you can just plug in some numbers to make sure that the things are aligned. So we can also combine all this stuff together. So how will we handle something that is little bit more complicated? Let's say let me just remove all this. Perfect. Okay, now let's say if I have to kind of calculate this thing, minus 2n plus 3. It's a little bit of complicated than the ones which we have already studied. So you have to perform the steps in a certain order, otherwise you will get the wrong answer. So the order you should always perform in such operation is shift and then flip and then escape. So it's a kind of a BODMAS rule, right, in mathematics, BMAS, BODMAS. So what you have to do is you have to perform the operations in this certain manner. You will and if you will perform in this kind of hierarchy, or kind of like step by step, like first shift, then flip and then scale, you will never get the wrong answer. and it's a kind of a like performing these operations in a mechanical way. So what I'm saying is, first you define the new signal. So for this example, let's say minus 2n of 3. First define a new signal. Let's say I define it z of n. So once I define the new signal, I have to first shift it. So let's say I shift the signal x of n by 3, because that's the shifting in the original value, n plus 3. So I shift it by 3. So it's like an advancing the signal. It's like not delaying it, but advancing the signal. Then I'm going to define another signal, which is let's remove some stuff. So then I have maybe I will define another signal, which is w of n, and I'll flip it. So this flipping means that I'll flip my z signal, because it's flipped here, it's minus, right? Then I'm going to finally get my result, which is y of n equals to w 2 of n, which is scaling. So first I have kind of shifted, then flipped, and then scaled. Now this y of n is basically the ultimate thing which I want. So let's see, y of n equals to w of 2n. If I replace this 2n by n in w signal, so it becomes kind of y of n equals to z of minus 2n, right? It works like this. So n, again, if I replace this n by minus 2n in the z equation here, what I get is that y of n equals to x of minus 2n plus 3. I think it's visible, but if there is not, let me know. I'll make a separate computation in the separate page and then upload it on the Google Classroom, which we have created. So you see that it works out. If I can just perform these operations in a similar way, I can just reach to the original thing which we have, the original questions which was already asked. So now I can just carry out these operations, right? So first operation is xn plus 3. So first let me just erase this thing, so we have some space. Okay, so you can let's perform the operation xn plus 3. So that means that my signal should start 3 units earlier. So this is my z of n when I am going, it's like starting from 3 units earlier. So you can see that it's minus 3 here, and now it's starting at minus 6, and previously it was ending at 5, but now it's ending at 2. So we have advanced the signal by 3 units. So this is my z of n. Then I am going to flip that around to get w of n, and then I'll scale it by 2, which means I'm going to compress it, and this is my final answer. So in case if you want to verify, then let's see what is y of 2. Y of 2 is basically x of minus 1, right? If you perform it like this, so it's like minus 2 into 2 becomes minus 4, and minus 4 plus 3 will become minus 1. But let's perform it first. So this has been like advanced with 3 units, then we flip it. So if we flip it, then it becomes a flip version. So it means that Previously, if you will see that it was at -6 and ending was at 2, now it starts from -2 and ends at +6. So the signal has been flipped now, and you can see that this thing has been here and this thing has been shifted here. And then what I'll do is I'll scale it by 2. I'll compress the signal. So once I compress the signal, I get this. So this is the compressed version of this. You can see that this one is there. Then I skipped one part, and then again this, and that I skipped one part, and then this, I skipped this thing, and then I retained this, skipped this thing, and then I retained this, something like that. Okay, it's like this one has been retained, and this one has been retained, this one, and this one. Okay, so this is the compressed signal. Now if I want to just check out that whether these computations work, let's see. I have y of 2 and it should be equal to x of -1. So this is my signal and y of 2 is this, right? Now let's check x of -1. So this is my original signal and x of -1 is this. So they are same. It checks out. Now let's do it another example. So if it's like if you want to verify any other thing, like let's say y of 1. Let's say I want to verify y of 1. So if you plug in here 1, it's like -2 into 1 is -2 plus 3, it becomes +1. So y of 1 is actually equal to x of 1. So if you will see here, y of 1 is x of 1, matches, right? So both the values match. It turns out that the computation is okay. And one more thing to be note here is that if the values are not provided, then the values will implicitly be 0. So if the values are not provided here like this, or the values are not provided here like this, so we assume that it should be 0. I hope it's clear, but if you have any questions, just ask me on Google Classroom or in our class which is scheduled. Okay, let's move to signal properties. So these signals look the same even when flipped. So basically the even signals, it's like if you have this kind of signal, it is considered to be even signal because it's a kind of symmetric. So you can see here that this is this, this reflects this, and this reflects this. So it's a kind of a same signal, but it looks like the flipped version of it. Now odd signals, let me write something. So even signals can be represented like this. So the original signal is equal to its mirror image, which is its flipped version. Now for odd signals, they can be represented by this, which is x of n equals to minus x of minus n. Now here you can see that this has been like flipped upside down, and this has been flipped upside down, this has been flipped upside down, something like this. Okay, so by definition, if I plug 0 here in the odd signal, what I get is minus x of 0, which is 0, which tells me that the entry of the odd signal is always has to be 0, and then it's kind of like a mirror image of itself around y-axis. Implicitly, every signal has one even part and one odd part, which means that even part of x of n can be computed by let's say this is the even part, and it can be computed by taking average of the original signal and its flipped version. So this is the even part, and the odd part can be computed by almost the same, which is the average, but we will take the even part and we will flip upside down as well, which is the mirror image. So let's see the MATLAB code for it, but remember these formulas, okay? So it will be easier for you to understand this concept. Now let's say I have generated here a kind of a variable, the random variable having 9 values, single column, single row, 9 values, and to make it interesting I have just subtracted it from 0.5. Now if I use stem, which is the stem plot, the by default plot, not by default but it's like the command for discrete plotting in MATLAB, so you can see that I have kind of generated a discrete time signal. Now you can see that the signal here is not even or odd, it's just random impulses. So we can just make it nicely. I would assume that the middle value is 0 and it can be done by giving the command as shown. So now if you see previously the scale was from 1 to 9 and it's like I want to make the middle value is at 0. So what I have done is I have just used this command, which is -4 to 4, which adjusts the scale. So now the center part is at 0 and the scale expands to -4 to 4. Now MATLAB has a command for flipping the signal, which is flip R, and it is like flipping from left to right in MATLAB. So the even part would simply be like, if I just make it like this. So let's say I use the even part, and the even part would be like the okay, let's first just make it flip. Okay, so let's say I name it as -x. So -x is nothing but flip LR and x. So once I do this flip LR x, the even part would be x plus -x, and this is going to be averaged, and this is the even part. So you can see that the generated signal simply obeys the characteristics of let's first visualize it. So this is the even part. You can see that it obeys the even part, kind of like flipping. And then if you this is the command for flipping. So this is the even part and this is the odd part. Now odd part is simply by writing it x minus -x divided by 2. So you can see here that the signal which we have already plotted or generated simply obeys the characteristics of even and odd. And if I want to verify that whether the signal is the original signal or not, what I can do is I can just add the even and odd part together. It's like adding even plus odd. So if I just add even and odd part together and I get the original signal back like this. So this is the original signal. I just like add even and odd part and I just plot it. So I retain my original signal. So it's also obvious from the formulas that adding even and odd results in the original signal. Something which is not immediately clear is why these formulas are guaranteed to produce the even and odd part of the signal. And that is your homework. So just try to search it out, just try to find out that why they are actually guaranteed to produce the even and odd part of the signal, and prove that this signal has to be even, like kind of this signal has to be even and this signal has to be odd, something like this. Okay, so let's move to the signal properties. Now another property is periodicity. This means that the signal repeats itself after a certain number of integer steps, like this can be mentioned as x of n equals to x of n plus n. So this means that the signal will repeat itself after n points. Now let's say I have a signal that looks like this, and I can say that the period of this signal is 4, because if you will see that 1 2 3 4, it repeats itself after every 4 units. So actually a constant signal is also periodic, which looks something like this. A constant signal by nature has period 1, so it just repeats, the signal just repeats itself after every 1 unit. You will notice that the periodic signals are super important to us, largely because we are going to deal with different kinds of discrete time sines and cosines. Now there are some special signals. Let's talk about them. So here is everyone's friend, delta function. Equally important is the step function. So in the delta function, it's like 1 at n equals to 0 and 0 elsewhere. So this is a kind of a delta function here. And then we have unit step function, which is kind of 1 after the 0 and positive samples, and 0 for the negative samples, which is n is less than 0. So this is like a signal which is off prior to 0 and then turns on at 0 and stays on, and it is usually denoted by u of n, where u usually stands for unit step. Now in this subject, it's important to have clear values on x and y, and here it is important to see that the value of at y-axis is actually 1 for all these signals. Now the unit step function and the delta function are related to each other. So the relationship is concerned with sums and differences, similar to the differential and integral in continuous domain. Also, you can think of the unit step function as bunch of delta functions. So by this analogy, the unit step function can be written as like this: sum of delta functions. So therefore, it's a summation of the delta functions from 0 to infinity, shifted by the value of k. So from 0 to infinity, it's like continuously. Why it is 0? Because at 0 it is like 1, and before that it is 0. So there is nothing before and there will be 1 afterwards. Now let's talk about these relationships some more. So in continuous time signal, if you remember, if you have a kind of a unit step signal, something like this, and if we take derivative of it, so the derivative of the unit step function is the delta function, because there is no change. It's like the change is from here to here, so we get the delta function, and from here onwards there is no change, so the difference is like 0 0 0 0, and similarly 0 prior to that. So the differentiation of the unit step function results in delta function. Now if you take the discrete steps, now it's the same thing. It's like if you take the unit step and if you take the difference of it, like this is 0 and 1 minus 0 becomes 1, and then 1 minus 1 becomes 0. So this differentiation is actually transformed to just the difference of the signal, like within the samples. So in this case, if you just shift the unit step function with one step, you will get this kind of plot, like this one is shifted from it's like 0 1 2 3 4, and this is 0 1 2 3 4, and there will be another one which is 5. So this is a kind of a what you say is a delayed version of this unit step function. And how we can like write this the equation for this plot, we can just write it like delta function is the difference of this unit step function and the delayed version of the unit step function, so we can get this. Okay, so this is a kind of a relationship in from continuous to discrete, and you will see that in discrete version or in digital signal processing the life gets easier because you do not have to deal with kind of integration and differentiation a lot for these kind of signals. Now similarly, if you will see here that the delta function was actually something like this, so it hops and then this, so this is the delta function. And the relationship of this is basically let me first erase the system. So the integration of all of the delta functions from minus infinity to a certain time step is the unit step function. Now if you take the discrete version of this, of course you have the only delta function here. And just now if I want to represent it in a kind of a unit step function, then I can write it as u of the unit step function is equal to k minus infinity to n impulse response. Now let's see, this is minus 2, this is minus 3, minus 2, minus 1 and 0, and 1 2 3 4 and 5. So if you have n minus 3, okay, so the summation of minus infinity to 3 would be 0 because impulse response is only active at 0, and otherwise it will be at 0 it will be 1 and otherwise it will be 0. So the summation from minus infinity to minus 3 would be 0. The summation from minus infinity to minus 2 would be 0. The summation of minus infinity to minus like this 1 would be 0. And then when you just insert 0 here, then the summation becomes 1. Now if you just kind of plug in 1 here, of course it will result in 0 at this instant, but the summation from minus infinity to this point will be 1 because there was 1 generated here. So if you sum it from minus infinity to positive 5, it will be 1 all the time. So this is the relationship of delta function and step function if you consider discrete time signal. So previously we discussed that the relationship of unit step to the kind of transformation of delta function from unit steps are a kind of difference from the differentiation, because in continuous time signal you have to perform differentiation, and in discrete time signal you can just use the difference. Now in continuous time signal you had to kind of perform integration, but now you can just perform the summation. So that's what I was trying to convey here, that it's simple. In discrete time signal you do not have to perform kind of complicated operations like differentiation and integration. You can just perform addition and subtraction here. So let's just end this session here. I'll upload another part of this lecture, but if you have any questions regarding the things which we have covered so far, please let me know in the comment section, or you can just ask the questions on Google Classroom, or you can ask the questions in my interactive seminar which I am going to conduct next week. Till then, stay safe. See you.